Hello everyone and welcome to another episode of Solving Advent of Code in Rust and try to learn Rust in between. I'm Roberto and we have
Luciano here, hello.
thank you everyone for following along. If you never did Advent of Code is a code challenge that is published around the Christmas period. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com and the new one is starting in days. So watch for it. We are publishing all our code in a GitHub repository, this one exactly. And also we have a YouTube channel that where we publish all the recording that you can find in the description of this Twitch channel. Last time we did exercise 22.
Two. Yeah.
Perfect. And we finished it. So today we're starting with exercise 23.
Should I share my screen and try to explain?
Yeah, share the screen.
Okay.
Let's read the README and let's try to understand what we have to do today.
So in the last exercise, we were basically challenging a crab to a game of cards. Now the crab is challenging us to another game, which I think is something where we need to mix some cups and then do a number of shifts and trying to guess at the end what is going to be the order of the cups. And there are different rules. So let's try to go through the rules and then we'll see an example. And I think at that point, we should have enough to cover at least how to implement part one. So we start with a label like this one, 3, 2, 4, 1, 5, which basically means that we have 1, 2, 3, 4, 5 cups. Every cup has a number, which is the label of the cup. And basically they are placed like in a circle. And you start from the first one, for instance, 3. And in the final game, we have to do 100 moves, but for now, that doesn't matter too much. Let's try to understand what are the rules for one single move. So basically, we are placing these cups at the beginning with a certain order. Every round of the game, we need to shuffle things around following these rules. So there is always a current cup, which is the one being pointed, let's say. And based on the current cup, the first rule says that we need to pick up the 3 cups immediately, let's say on the right.
Yeah.
Imagine that this is circular. So, of course, you can place it in a line, but of course, you might overflow and then you need to go back at the beginning. So this is why here is saying clockwise. But you can imagine it as a line. And if you reach the end of the line, you start back at the beginning. So what happens is that you take the current cup, you take the next 3 ones, and you remove those 3 ones from the list or the circle. Then we need to select a destination cup. And there are rules to do that. That is going to be the cup with a label that is equal to the current cup, -1. But it could be that this is one of the 3 that we just removed. So what we need to do if we cannot find in the current list a cup with a value of the current cup -1, what we do basically we keep going, decreasing 1 until we find a cup that is still left in the list. There is another edge case. What happens if we reach there is no 0, but if we reach 1 and we do -1, basically we need to go back in circle. So let's say that here the last number is 5 in this example. That means that we need to continue again from 5 and then keep decreasing from 5. So eventually we should find a destination cup based on these rules. And once we do that, we have the 3 that we removed. We have the current cup. We have the destination cup. What we need to do is we need to place the 3 cups that we removed so that they are immediately clockwise of the destination cup. So that means on the right of the destination cup. And I think that at that point we finished one round. We just need to move the cursor for the current cap, which is going to be the cap which is immediately clockwise of the current cap. So basically we shift the position of the current cap by one. So just to recap the rules, I mean, I'm not going to recap the rules, but just to give you an idea, is we have a list. We are selecting one element. We take 3 elements. We remove those 3 elements. We define where to place those 3 elements again, and then we shift the cursor for the current cap. So every round we're basically removing 3 elements, but also re-adding them in a different position. So that's kind of shuffling things around a little bit every round. And here there is an example where we have, for instance, if we start with this string with 9 caps, and we have all the numbers from 1 to 9, we start with this configuration, the one in parentheses, the one we select. Then we pick up the next 3, so 8, 9, and 1. And then we need to find the destination cap. So the first value we need to check is this value minus 1. So it's going to be 2. These 3 are removed. So the first one we find is actually 2. So we found our destination. That means we take these 3 and we move them just after 2. So our result at the beginning of the next round will be 3 and 2, and all these 3 that we remove just after 2. So 3 and 2, 8, 9, 1, and everything else remained unchanged. And we keep going applying the same rules. And after 10 rounds, we will have a specific configuration, and this is going to be our answer to the challenge, even though I think the challenge is asking us for 100 moves.
Is, give me all the numbers after the 1 in the order you find them.
But we need to simulate 100 moves.
Yeah, but with 100 moves, yeah, exactly. And our input is different from the example.
Okay, that's perfect. We already have comments. Oh, hello, Tommaso. Day 23 is the hardest, I think. It doesn't seem too bad. I think we have seen worse.
I still think that is the 20, the one with all the images and the ties to rotate and everything else, the worst.
That one was pretty tough. We spent, I think, 4 episodes before we fully managed to...
3 or 4,
before we fully managed to complete that one. So, yeah, let's see if we can do this one, at least the first part, in 1 hour. Okay, so let's keep going. Roberto, did you want to show your slides where you were showing maybe the flow a little bit better, or do you think that makes more sense for part 2?
For part 2 makes more sense. I think for part 1 is smaller and simple. It's the same algorithm, it's just smaller, so we don't need anything fancy. But it basically is a graphic representation of what you just explained now. So
okay,
it's not adding anything.
Okay, then for part 2, maybe we'll have a better look because we might also optimize a little bit.
If we do that next time, we have to recap what we have to do at the beginning of the stream.
Okay, so we have our usual scaffold here to get started. I was actually spending a little bit of time thinking about what could be a little bit of a more idiomatic solution, based also on the suggestions that we got in the previous episodes. And I'm thinking that what we could do is to use 3 different traits: the iterator trait, the from string trait, and the display trait. So basically with the from string, we parse the input and we create a state or a game struct, if we want to call it. That game struct is going to be an iterator where at every iteration, we basically simulate 1 turn of the game. So we shuffle things around for 1 turn. And that allows us to write tests for every turn. So we can check that the state is changing as we expect. And then finally, we can run a certain number of rounds. We will need to run 100 rounds for the actual exercise. And then at the end, what we can do, we can use the display trait to just do a 2-string of the entire game state, and that should give us the answer, which is basically the list of numbers in the final order. And yeah, Tommaso is always a big fan of this approach, so he's already suggesting to do something like this, and this is pretty much our idea. Okay,
So
we
our
also
state-
have a
our-
question here. Are you all learning Rust? And that's why Rust? Yes, definitely. Yeah, we have been forcing ourselves to do these live streams every Monday as an excuse to practice a little bit of Rust.
And that's why it's 1 hour long, because if it was JavaScript or Python, it was 5 minutes. So
especially for
5
Roberto, if you give him a problem in Python, he will solve it in 5 minutes. Okay, so do you think it makes sense to go with this approach? And
yeah, let's create a struct with our current state that is the list, the vector of
what
list
do we
state.
call it? Game, I guess.
Is the game state in that moment.
Let's call it game state. I like it more.
In a specific turn. And it has a vector of
ups, right? Back. What do we use? U8 for now because they seem fairly small.
we have a number between 1 and 9 at the beginning, so I think U8 is enough.
And then we will have a pointer to the current cup, so we can probably use, I don't know, current, I guess, and usides.
Yeah.
And then I think that's probably it. I don't think we need anything else.
The single state is described by this. Then when we implement the next function, the function that do the cycle, there we need other variables, other bit and pieces, but let's think about them. Let's start with the parsing.
Exactly. The first thing we want to do is to implement the from str, which for game state, and that should be fairly easy. Implement missing item, error. And then for now, we can just keep it empty. We are not going to do proper error handling. And missing member is from string. Okay, so here what we want to do is
show our input.txt file. So
oh yes, you're right. This is the actual input, which is just
1 line, 1 string, 10 numbers. No, 9 numbers, sorry.
From 1 to 9 without repetitions. Exactly. So what we want to do is let caps, which is going to be a vec of U8. Probably what we can do is just to do s.chars dot map, I guess.
Yeah, we have to map them to integers.
And we need to do C, and we do C into or parse, I guess. And unwrap. I don't know if this is going to be able to infer, but let's see. And then we do collect. Let's see if that's no, it's not able to infer, so we'll need to give it a little bit of a hint.
Can a char become a U8? Or just a string can become a U8?
I thought it could.
Or you need to convert the char to string and the string to int?
Maybe we need to do into. Okay.
We did a trick C minus the value of 0 last time when we did the parsing for the it was the expression parser. That was exercise 17 or 18 in my opinion. I don't remember.
Let's see that trick.
I'm not sure of the numbers, so if you open the input file, it's easier to understand if it's the right.
Let's see, input.
No, before this one.
No, this is 23, so 16. Was this one?
No, 19.
Maybe this one.
Right, there were expressions. Do you remember when we parsed all the expressions? Go to 19. Sorry for a moment, because I'm still.
This one
No.
maybe.
No, okay. At this point, I'm lost.
Okay, let's search for it. I mean, it must be easy to do. Convert a char to U8 Rust.
Sorry. And it was 18.
It was 18. Okay, let's check it out very quickly.
The only one that we skipped, obviously.
Oh, 0. Yeah, that's how we did it.
Yeah, but now we have to do U8 instead of U64.
Okay.
Because there
By
we
the
were
way,
parsing.
in the chat, if you know any better way, let us know.
Yeah, thank you. Because this is very C.
Exactly. Okay. So this will be as U8 and minus 0 as U8. Okay, that is something that it likes. So we should have our vector of U8, and now we just need to return.
No, we have to set current also. Okay, yeah, we are setting it here.
Game state. Yeah, I'm just creating it in line.
Yeah,
and caps, and current is gonna be 0 because this is the index of the first item.
First element of the vector.
Now, why doesn't like this one? Casting a character to U8 truncates it.
Because it can be UTF-8. So go with U60, U64, and then we can collect. Or we change our caps to be a vector of U64. So it's even useful for part 2 because part 2 will be with huge numbers. And I don't think that memory-wise this is changing a lot.
And collect U64, and this would be U64. Okay. Now, if we want to write a quick test, we can just do, I don't know, test from str. And what we want to test is basically let state equal of game state equal a value, let's say, I don't know,
1, 2, 3, 4,
5. Yeah, this.
Yeah.
And parse, unwrap, and then we want to assert equal that state dot caps that I think state, and here we can probably just say vec of 3,
4, 5, 6,
7, 8. And that seems good.
That's a wargaming, okay.
Because we are not using this one yet.
Okay, no, we are.
Okay, so the next thing is where it gets.
Do you want to implement the display, or?
Actually, let's implement the display because it's easy, and then we focus on the business logic. Display for game state, and this is gonna be, give me the autocomplete because I don't remember the signature. Okay, here what we want to do is basically do write of f, I think. There is a formatter here.
Where is the formatter? I get lost.
Why is not called f? Yeah,
and then what was called? Sorry, underline.
Yes, I don't know why.
Okay.
And then we need to do self dot caps dot either dot collect. Can we probably need to map to chars.
Can't you join a comma, convert it to a vector of strings and join on comma?
You might be able to do it if you convert it to a string of chars. Sorry, to a vector of chars.
Well, vector of strings.
Map.
Because so it's also usable for part 2 if you do a vector of strings.
Right.
So
yes.
map X.
So we can do basically string from, right? That should do it, and then we do join.
With
Why
a comma.
Join doesn't work? And then collect. This is what I was thinking.
We join with a comma, with a space, because if you join on nothing, we attach all the numbers together.
Isn't the answer without...
But the answer wants a number. It doesn't want a string, I think.
Really? Oh yeah, you're right. So we just need to build that number.
When you have the string, you just do parse numbers. So.
Okay, I was thinking that we needed to return a string, so maybe the display doesn't make sense. We can just have a function in the game state.
It's useful for us, probably for debug the display.
Well, but at that point, we can just implement here debug and we'll see it, right?
Okay.
We can just derive.
So, comment
okay,
or remove the display.
Let's scrap this one, and maybe we'll do a method that is result or whatever we want to call it.
Yeah, we implement a specific method to get the result
out. We can do implement game state, and we do fn result, and that takes a reference to self, and it returns what it returns. Usides
number. It's a number.
Here we said usides, but we can probably change it.
Usides is fine for me.
Okay, and how do we build this number? I mean, we could effectively multiply every number in the vector by its position, right?
If you read the README, we must find the one, not to take the one in consideration, so don't care about the one, and start from there looking at the numbers.
Oh, I didn't realize that. So that basically means, let's take the last example. So this is the final configuration. The number that we need to return for this configuration is?
Producing, you see, on line 80, that is quite long. At one point, is producing.
There, okay.
926. If you see, one is there, and then you start now 926. Whoop,
and you wrap around. Okay.
Yeah, we always wrap around because we are in a circle in reality. But we don't output the one. So we have to find
9 to 6, all of this. So
we have to find the one in our vector. From there, we just have to take the number that is next to it and add it to our result. Multiply by 10 and take the next number and add it. Multiply by 10, take the next number and add it.
Let's do that.
Remembering to wrap around. If we arrive out of bound of the vector, we have to go back to 0.
So what we want to do is basically...
we have to find one.
Let's see, how do we find one? If there is a find method. So let pos 1 is equal to self.caps find. Is there a find?
Index. Yeah, index.
What does it do, index?
No idea. No,
I don't think it does what we want. No,
it's not that one.
Let's see if there is a find. Oh, Tommaso is suggesting enumerate, but enumerate could make sense if they were already in order, right?
We don't have to change the order. We have to go from the first one. So from the one with 1, not the first one, with the one with 1.
There isn't a find. I am surprised. Maybe we need to do either dot find. Okay. And find what is it going to give us? An index, I hope. What does it return?
True or false?
Option U64.
No, what is returning? Oh my god.
Then we need enumerate as well. Yeah, I think Thomas is right.
Sorry, I'm getting lost. It's not giving you back the index of the element.
You need to enumerate, and now you get the index and the value. And the predicate is basically that the value is equal to 1.
But
Right?
the value is a tuple. The value is the index and the value. So
right, the value is, you're right. Let's do underscore
comma iv. And okay, and in this way we will have back a position and value. So let pos1 can be let pos1 comma underline.
Cannot compare a reference, okay?
Guys, is
Seriously? Do I need to dereference twice?
Or you have to reference to the one?
Okay, whatever. That's fine. Okay. And then we unwrap. Now this one is gonna be position
comma underline, because we know that the value is 1. We are looking for that. And now position is a usize. Perfect. Now we know that we have to start from position +1, remembering to wrap around if that +1 go out of bound. So
okay, so and we need to get up to position 1 again, basically.
Yes. So right? Our position is position 1 + 1 modulo the length of the vector.
So current position is pos1 plus 1 and all of that.
Everything modulo the length of the vector.
Self dot caps dot len. Okay, and now we do a while.
While current position is different from pos1.
Is different than pos1.
Perfect.
And now we also need to have a counter for multiplier, right?
No, it's not needed.
No?
No, because it's the fantastic trick of parsing numbers. Accumulator multiply equal 10.
Oh, you're right. Multiply equal 10.
And
but then we also need the current number, right?
Semicolon. Accumulator plus equal the current number, that is self caps of current position.
Forget current position.
We need to unwrap this again.
Yes.
Okay. Now current position plus equal 1 and modulo the cap length.
Perfect. Yes. Current position plus.
So we have to make current position mutable.
Yes. Good point.
Because
we are accumulator mutable.
Yeah. Yes.
And I wonder. Let's do this.
+1.
I'm not sure we can do all of that like in. Let's do it this way, so it's only one go. And mode self.caps.len.
This way we wrap around if we go out of bound on the right. And this,
why doesn't like this? Because this is probably a reference that we need to the reference.
Because it's in U64.
Oh, so we need to say as you sides.
Yeah, probably. And now it's complaining.
We need to the reference, I think, all of this.
And then cast it.
Okay, perfect.
Oh my god. Now we can create a test for this.
Yes, so we do a test where we test the result. Test. What we do.
You have to put a 1.
You need to put a 1, yes. Yeah. So let's do 1, 2, 3, 4, 5, 6, 7, 8. Let's put a 9 as well somewhere. Okay. So what we expect is that if we do state, so assert equal. if
all
we
the
do
star imply a
state
copy,
dot
state item.
result, we get what? 2,
2, 6, 7, 9, 8,
9, 8, 3,
3,
4,
4, 5.
5. Yes.
Tommaso was saying that every time that we use a star, the referencing, we create a copy. It's true that it's a copy of U64, so I don't know if this is bad. We can address that later, probably. Also
okay, we also have Arcade Soft, the arcade soft, that is asking us to do a rep. Let's see if we manage to write the solution in 1 hour, maybe we'll consider it.
Rep? What?
Rep song, I guess.
A rep
right?
song. Okay, are you sure?
I don't know.
Let's
run this test. Okay, works.
I'm not emotionally ready to sing.
Okay, so we have our result. Perfect.
Well, now let's do the true job. So writing the change of state, the next state.
So let's implement iterator for game state. Now give me auto completion powers, please. We need another thing.
The type for the error.
No, for the return of every single iteration. I suppose here we could return a tuple of. Let me show the README just to be clear. One thing I was thinking is that we could write a test for every step. So for every step, what is interesting is the items we picked up and the destination. So these are maybe the things we could return.
So we can return 4 integers.
Or we could return a tuple of 3 items as
a tuple
an array.
of a tuple of 3. No, they're always 3. Why an array? Return a tuple of a tuple. Can't you?
I suppose we could. I was thinking something like this, where we say U. What did we say? U64.
U64 3, comma,
and then U64. That's what I was thinking.
Okay, fine.
Okay, so now let's start by. So we know what is the current, right? So the first thing we need to do is to take the first 3 items.
Yeah.
After that,
that will be vector caps of current plus 1, vector of caps of current plus 2, vector of caps of current plus 3.
But
remembering always that we have to use the modulo to wrap around.
Okay, so let's do let. Now do we want to pick up the indices? I suppose it's interesting now to see what kind of methods do we have in vector to be able to.
We have to pick up the values and extract them by the indices.
I'm thinking because we'll need to mutate this array.
Yeah, we need to mutate the array. So we have to take out the values so we can override them.
But I don't know exactly what kind of methods do we have to take out values from a vec. And also, do we want to take them out one by one by mutating the vector? Or do we want to keep kind of a copy of the things that we want to change and we only change them? We
want to work in place or we want to locate more memory? You know that we are always going for the dirty solution.
Exactly, yeah.
So do you want to play it very dirty?
Maybe.
Okay, let's do this. At the first, before starting, we always, we don't care about our current position. When we start, we always roll the array so that the element 0 is the current, and then we know that 1, 2, and 3 will be the one to remove, and 4 will be the one to shrink. So what we can do is creating a vector, slicing out from the original one everything, and just keeping the first element and the one from the 4 going on.
I have another idea that is coming from Tommaso's suggestion here, which was saying just do dot remove index 3 times. Of course, we just need to make sure every time that the index is still inbound, otherwise it needs to wrap around.
Here is the dirty idea. If after we do all our turn, instead of moving current, we take the first element and we put it as last,
Okay.
the current will always be the one at index 0.
But we are doing one more vector manipulation for no reason.
Yes.
I mean, I think it's better to just increase a variable, right?
Okay, let's go that way.
Then we have another question, which is, when do you finish the last advent of code? Will you start the new of this year? Probably yes. We haven't decided yet because we are focusing on finishing the 2021s, but hopefully we will finish them in the next 2 or 3 episodes. So we can probably...
there is 23, 24, and 25 is only half day. So we hope to, we can start. The only stuff that I don't know is that if we want to start when they are still out. So I would wait for them to finish. I mean, when Advent of Code is over in January, we start with Advent of Code 2021. Just to not spoil the solution for people while it's still open. If you understand what I mean. But well, to us.
Okay, so this is the one where we want to start removing from that position, right? From that index.
Current +1 length, yes.
And now what we do is basically...
we remove 3 times from that index. When you remove, the vector is going to shrink.
I'm curious also if it gets returned. So if we do self.caps.remove and we say to remove, what is it going to return?
64. So yeah, it's giving you back the value. There is an explanation probably down.
Removes and returns the element. Okay, perfect. So that's what we want.
So if we run it 3 times, we will have the 3 elements with the same index because it's moving.
Yes. So we'll need to do this one again.
You can assign, you can create the array of 3 elements and assign to them.
No, I'm wondering if we'll need to consider that we might be wrapping around. So if this to remove also needs to be modulo or not. Because of course, every time we remove the array, it gets smaller.
Yes.
Right? So if we remove the last element in the first step, we still need to remove other 2 elements, that they will be the first 2 on the other side, right?
We have to go back to 0. Yeah, so, if to remove is bigger than the length, greater or equal to the length of the caps, we have to set it to 0 and remove from 0.
Yeah, I'm wondering if just doing this is enough. Is it going to be enough? I think so, right?
Probably yes.
And then what we can do is essentially do this 3 times. So we can just do what do we call it?
If you create the array that we need to return with the elements.
Yes.
Pick up.
And this is going to be, actually, we can just do this, I suppose.
Yeah. Comma.
Oops, wrong copy paste.
Okay.
Right.
Okay. Now we have to find the destination on what's left of the caps.
Okay, so let's say let expected dest, or let's say actually dest value. And this initially we know that is the current. So it's gonna be the value of the current item minus 1, right?
Yeah.
So we want to get the current value first because we don't really know what it is. So self.caps.get self.current up minus 1. And now it's going to complain that, oh no, because...
Why?
Okay. Yeah, because this is going to give us a U64. We do minus 1, and this is a U64 as well. Perfect.
And we have to look for it in the vector. If it's not there,
now how do we look for it? Do we use a find?
Before we use the find, but here we cannot find it. Also, that self-current can be out of bound, but we address it later. Because
I wonder if we can do something like while let
contains.
sum.
There is contains on the vector.
There is
contains.
Yes, there is self.caps.contains. Yes.
Yes, this is not very optimal from the big O notation point of view, but we don't care. They are 10 values.
Or the alternative is we just loop and then we break.
Okay. Yeah.
What do we need to keep though?
No, destination value is enough, and we have to find it in the array. If it's not in there, we have to look for destination values minus 1.
Okay, so that becomes mutable.
Yeah.
And what we do is basically if, but we need an index, right?
We need the index where that element is, if it is in the array. If it's not, we have to go and loop again with with this value smaller than 1. If we roll to 0, we have to go back to 9. We have to roll back to the...
Yeah, that's why I don't think we can use a find, because we need to do this kind of looping around ourselves. Otherwise, the find is always going to start from the beginning. But instead, we need to start from a certain index to the right and then go back to the left. Right? So, and the index is the current position, right?
You can start from where you want, to be honest, because if we have a 3, we are looking for a 2. If 2 is not there, we look for a 1. And 1 can be in any position. We don't care. It's always on the right of the cap because it's a circular. It's always on the right. Because there is always something on the right.
You're right. Okay, I don't know why
even if 1 is on your left, in reality it's on your right, just a lot on your right.
Okay, so you are perfectly right. So what we could do is literally just to let what do we call it, destination equal self dot caps dot iter dot no enumerate dot find.
We need the index. Sorry. And now we have.
Is there like a find by value? Maybe find.
No, it's fine.
And we want to do value
and index. You need to take 2 of them, or do v.0 then.
I and v. And what we want to do is that v needs to be equal to that value.
Obviously, here now we have to the reference what? No, nothing. Now that's the comma underline because we don't care about the value, and the I that you use in the find can be an underline.
Yes. So here, what I'm wondering is,
but
basically while dest is none. I am sure that there is a better way to write this. We'll need to do the same, basically.
We have to decrement dest value and then search again, because if we don't decrement it...
exactly, then it's an endless loop.
And if dest value is 0, is 9.
Good point. If Test
There are no
value.
0 in our stuff. So if it's 0, it roll to you the biggest that we have in the vector. You can take the vector max, or we know that is 9 for our example. Probably for part 2, we have to make this parametric.
Can probably do. I'll leave it like this. We could probably join these two in an if else, but this is probably more readable.
No,
Okay.
This is not real. Yeah. No else movement,
Now,
remember. Avoid
now
else.
again, double star. Sorry, Tommaso.
At this point,
here we know the destination index. We just need to reinsert.
You don't need the let on line 35, and you have to make a dest mutable in line 29.
We need to do
line 35. Remove the let.
35. Okay. Oh yes, because otherwise we are not reassigning.
And line 29 make dest mutable.
Line 29. Yes. Okay. I don't know why it's not complaining. Cool. So at this point, we are almost done. What we need to do
know the destination. We know the index of the destination, because dest is the index of the destination. We have the free values that we have in our array pickup.
I mean, at this point, we can return the 3 values, right? So pickup.
Yeah, pickup and dest. Before returning, we have to insert the elements in the vectors in the index dest +1, because they must go on the right of dest. So always remembering to roll if we go out of bound.
Yes. I wonder, can we go out of bound?
If dest is the last element of the vector, dest +1 go out, and we have to go back to 0, because we have to add them on the right of the last element that is the first element of the vector.
Okay, so what we do here is for value in pickup.
Probably pick up from the last to the first, but let's try. That's because you're putting in the first one in 0, then you put the second one and you move the one that you have in 0 the right, so they get in inverted if you do in this way. Can you reverse pickup, or?
I think so. I think at this point we get the values. Yeah. Okay, so now what do we do? Self
cap insert. There is an insert.
Insert
the inverse of remove. Okay, yeah.
Okay, we need to specify a position and a value.
Our position is dest +1 modulo the length, again.
With parentheses.
Yes.
I can type modulo self.caps.
I think probably this number can be computed only once before the loop, because the length is changing.
Value again is going to become a copy because we do a star, but that shouldn't be a big problem.
Okay, dest +1 modulo that piece. Can you compute?
Yeah, dest. We need here to do this.
Yeah. So dest index
equal dest dot unwrap.
And then it's only the
and then it's only the first one.
Yeah, only the first one.
Okay, so let's do
dest index. Let dest index equal
this, right? And then we want dest edx. And now this is gonna be happy.
Dest edx. Dest edx +1 modulo self caps len. That expression.
Wait. Dest edx.
Is a usize because it goes in an index.
Yeah, so why don't we just return a usize here?
No idea, because we don't like the usize.
Okay, it's still not happy. Why? Found. Oh, it's an option, expected option, of course, because of. Yeah, so we just need to say some of this. Because an iterator is basically eventually could finish and you return none.
Yeah, in our case, this one can't finish because of the rules that can go on forever.
You can keep going, yeah.
I was saying on line 44, dext plus 1 modulo the length, just that piece, the first parameter.
The first parameter, yes.
Take it out in a variable in line 42.
In line 42.
Before the loop.
What do we call it?
Dest index plus 1. I don't know.
Target.
Yeah, target. I like target. Target index.
IDX. And
let the target EDX equal what you have in the. Okay. I'm not sure if everything will work. I still think we can have an out of bounds somewhere, and there is something in line 29 that is complaining.
Oh yeah, you're right.
Again.
Is it again the cool? And we are not using it, so it doesn't matter. Okay. Let's.
What once Tommaso is asking if we have to return dest or target IDX. What say the README in the examples? The
destination.
It's not returning the index of the destination, it's returning the value of the destination.
Oh, yeah, right. Okay, let's do that. Shouldn't be too hard, right? Because we actually have it.
We have dest value. So we return dest value.
Yeah, exactly. And that one is decreased properly.
Yeah. And this value at this point is a U64, it's not a U size. For this reason, we were returning a U64.
Good catch. Now we should be fine.
Okay, let's try one step of the README in a test and see what's up.
So let's do a test. Let's call it test game P1, I guess. Or test iter.
Yeah, test iter for one step.
So we need to create this particular game.
Yeah.
So we say let state game state equal this, which
remove
format properly.
Yeah, remove all the garbage.
And then dot parse. No.
Yeah.
What did I do?
Multi-cursor strikes
parse dot unwrap. Now what we want to do is
one step.
Let what did we call the pickup and test equal state dot next dot unwrap. So we are basically saying do one iteration, and we are sure that that iteration is going to happen because our iterator is endless, so we can unwrap safely. And now we can assert. So assert equal that pickup is going to be these three values, so 8, 9, and 1.
In an array. Okay, yeah. There we go.
And then that, this needs to be mutable. Of course. And destination needs to be 2, right?
From the README, seems so. Like I said, we could have one out of bound problem. If we land in it, we'll fix it.
Okay. Current position is incremented in the next function.
No, he's right. We have to increment it before returning to create a new game. If you go back to our
implementation, okay.
Yeah,
he's right. Here.
Yes, we are not incrementing the current position. Before returning, we have to increment the current position by 1.
Oh, right.
And the modulo, because otherwise...
current plus... is equal.
Self current plus 1 modulo length, self caps length. Good catch. we were forgetting.
Okay, so let's see if one iteration works.
I don't believe in it, but
It did.
let's try 2 iteration.
Also, we have a bunch of rubbish here. So display and ops index. Do we need it? I don't think so. Now let's try 2 iterations. So let's do another round. So we do again this. And now we need to assert. Let's see, what do we need to assert?
Let's go to readme and take a look.
So we do expect again 891 and position 7.
Okay,
So
we
that's
can try.
kind of easy.
Try another one just because
Wait.
life is hard.
Okay, that was good. Now let's keep going. 4, 6, 7,
And 3.
and 3. Okay, now with Explorer.
And now we have an out of bound. Where is the guy?
I've tended to subtract with overflow in line 36. Let's see, what do we have there?
Subtract
There,
it over.
destination value. Oh, yes, this one. So I need to do the else thing that I wanted to do.
Sorry. A moment. Dest value is a U64. So obviously, if we try to go below, but if we are at 1, we go at 0 and we go back at 9. How can we be at 0? Because we are doing -1 on line
I was
29.
doing it before. Yeah, I was line 29.
28 now because you moved stuff, so it changed. In line 28, we are already doing the -1, but we are not checking if we arrive at the dest value of 0.
Oh, right.
We have to check it also. You don't have to change the if there. You have to change to add an if after that one.
After this one?
After this one, we have to do if the dest value is 0 is 9. And you can leave the stuff inside the while like it was.
But then this while will keep going.
Yeah, put back the while how it was. Perfect.
Okay.
Take that if, just that if, and copy it after line 28.
But not cut it, just copy it.
Copy. Try now.
Okay.
I missed that we were decrementing also there. And now we have an out of bound where?
No, now it's just giving us different values. In which one though? Wait. The third one. Did I copy it correctly? Let's check. So this is the third iteration. So move 3. We expect 4, 6, 7. And instead we get 3, 2, 5.
3, 2,
let's do
5.
Println of
ODBG.
It's the same, I guess.
Okay.
So now we should visualize what is the state before running the next iteration. Yeah. So test this guy. Okay, so the state is this one, and current is 2. So it's gonna be, this one is gonna be the current. It should pick 3, 2, and 5. Remove them. It needs to look for 2, but 2 is not there. No, sorry, it needs to look for -1, right? So it goes 9.
Yeah, but that's...
So it will find the 9. And it needs to re-add 3, 2, and 5 after 9.
If current is 3, -1, it goes to 2. It's not there. -1 again, it goes to 1, but 1 is there.
Wait, but we are failing even before replacing these things, because here in our logic we are saying we expect to get 3, 2, and 5, and this is what we are failing, right? Because we are saying for 6 and 7. So I think
that-
we
I
might
think
have
that-
broken the previous one.
Yeah, I think that state, if you take that state 8, 9, 1, 3, 2, 5 is not the right state.
Exactly.
Go back to the README. No, it's enough that you go to the read. Yeah, you print.
I'm just curious to see where things start to diverge.
Yeah.
If they start to diverge even at the first step. So let's take this file, the README, and compare. So initially the state is correct, and current is 0.
Yeah, the second state is correct. Yeah.
The second state is 3, 2, 8, 9, 1, 5, 4, 6, 7. Current is 1. Okay. So what is going wrong here? Why this is different? So 8, 9, and 1, they are inserted after 1, right? Oh, they are inserted before 1. Is that correct?
8, 9, and 1 are extracted, and we are on 2. They must be inserted after the 7, and instead we insert it after the 2. Because, here is the out of bound that wrap back and we fuck up.
So basically here the target is 7.
Yeah.
So does it mean that we need to insert these 3 numbers
in the last
before or after 7?
After 7.
Okay.
And if you see the move 3, they are after 7.
So when we reinsert the items, we never need to wrap around, basically. We just push them at the bottom.
We wrap around. Okay, our problem is the following. We've wrapped around. We added 8, 9, and 1 at the beginning of the array. That is fine. But this pushed our current along the array. So our current is no more 2. Because we added the 3 element at the beginning of the array. So our current must be of an index that is 3 elements on the right to where it is at the moment. For this reason, I was suggesting of always slicing the vector to have it that start at 0, so we don't have to deal with going.
Okay, I see what you mean
beginning
now.
Again, because it's correct. The state is correct on itself because 8, 9, 1, 3, 2, 5, 4, 6, 7 being circular is the same that you have at the beginning of move 3 because it's just rotated by 3 elements. It's perfectly fine. The problem is that it's our current element that got moved and we didn't update it.
Yes. But I'm wondering if we just push all of them here. Is there going to be a problem? Like rather than moving the current, if we don't wrap around when we insert the values.
Let's try. Let's try not to wrap around when we increment the destination.
So basically, where is it?
Target here. Destination, line 753. Don't modulo.
So we remove all of this here, right? And that's
Just it.
Okay, let's see what happens. Brace for it. Works. And do we get exactly the same value? I think so. 3, 2, 5, 4.
Yeah, I think it's the same like the README at this point.
Okay, I suppose at this point I'm just gonna copy paste all of it and do.
Okay, let's try. Finally, is just
crazy stuff there. Ooh, beautiful. Okay, so what do we do? I'm not gonna keep copying the state. So this one is 913 and 7. This one is 6, 7, 9, and 3. And now 3, 6, 7, and 9. Three, 6, 7, and 8. That was almost the same. And now 5, 8, 3, and 1. I know this is super boring, but at least we have a good degree of certainty that everything works.
I still think that we have an out of bound in a specific edge case. We'll see.
Okay. 5.
I'm still waiting for that out of bound.
And then we have 7 for 1 and 3. Oh, that's the same. And 3. And now we can even assert on the final state. So assert equal.
Well, just print it for now.
That state dot caps is equal to vec of all of this. Remove this, and we do the fancy multi-cursor. Is it gonna work? Let's see. Yes, it panicked. So it panics in line 125. So that is here.
We have some math that is not with indexes that is not working properly.
So let's again, let's do DBG because I'm lazy. Let's see. Let's see the last two. Okay, so current 3. What did we expect? If current is 3, it should take 6.
No, well, that is 2.
Sorry, 7. And the 3 values are 2, 5, and 8, which is what we are actually getting, but we assumed we will get 9, 1, and 3.
That are around the wrap of the...
So let's compare which... Actually, let's do something. So this is... do we call it 1 here in the README? Move 1. Okay, so let's keep doing this everywhere. Move 2, 3, 4. 4 is where it gets wrong, right? So if we run this one, we should be able to compare 1. We knew it was okay, right? It's still the same. 3 to 7, current 0. Then 2 is 3 to 7, and current is 1. So that looks good. 3 to 8, 9, 1, 5. Yeah, that is good. Now move 3 is 3 to 5. 3 to 5, 4, 6, 7. 4, 6, 7, 8, 9, 1. And current is 2. Now move 4 is where things go wrong. Why? Current is 3, and this is where it's wrong, because this is starting from 3. Instead, here is starting from 7. Why? Let's try to compare these two steps. So here it got 4, 6, and 7. And decided that the destination is 3, which is here.
Because we are pushing elements before the current. And
we are not wrapping around these ones.
And when we push stuff on the left of the current pointer, we have to move the pointer. Otherwise, we are not pointing with current on the right element next time.
Mm-hmm.
Every time we insert on the left of our current, we have to increment current. If we insert on the right, it's not a problem. If we insert on the left, we have to increment current.
Yes. Let's do that. So this is an edge case, but I also suppose
when we insert on the left of the current, we have to increment also current.
Mm-hmm.
That is, we can do that in our for loop. That is in line 54.
54, yes.
If target index is less.
Before or after? It doesn't matter, right?
Inside the loop.
Is less than current.
No, but we can do this. We know that the length is free. We can do this outside of the loop, to be honest.
Oh yeah, we increased by 3.
By 3 or by 4? By 3. Yeah. If the target index is less than the current.
And, is it called current?
It's self.current, I think, because.
Oh yeah, that's why.
We are inside the object.
Then
no, the struct is not an object, it's a struct in Rust. Sorry. Plus equal
3.
The modulo will be done in line 62, so we are fine. Here I'm thinking if it's +2 or +3. I think it's +3, but let's run the tests.
Now the last test is not going to match, the last assertion, but everything else might work.
Might.
Is it just the last assertion that didn't work?
I don't know where we arrived.
I stopped even printing. Okay, let's keep going.
It doesn't say which is the line.
It does say, but let's do this
okay.
quickly, because I changed the line anyway now.
More than asserting what is the final state, you can assert what is the final result.
That's true.
That is.
So this is 9.
Not caring about the vector sorting.
Yeah, we could probably normalize this one, but doesn't matter.
The result is normalized in that, but okay.
Oh yeah, you're right.
So where is in panic?
In 4. Is panicking in 4 again. Why?
Let's read. Unwrap on line 28.
28. What do we have there?
Yeah, that was the one that I was expecting out of bound. Because the current, if it is basically, if we remove a free element and our current is, let's think that our current is the last element of an array. Okay, and we are removing free elements. The array is getting shorter by 3.
Yes.
But you are pointing here, and you are pointing outside of the array. So if you are here and we remove 3 elements from to remove, that is on the left of our current must be decremented. It's the same logic as before. If to remove is less than current minus equal 3.
Okay. And to remove is
before line 28.
Yes.
If to remove modulo capslen, it's already modulo capslen to remove. Why we are modulo them again and again and again? Well, if to remove is less than self-current minus equal 3.
Self-current, yes.
Must be moved on the left by. If we insert on the left, we have to increment it. If we remove from the left, we have to reduce it.
Right. Okay.
And if it is okay, we can have another edge case. No, we can't have it, or we can. Or can we?
Does it need to have a modulo?
I'm thinking about it. Let's think that you have an array. You have current that is not the last one, but the one before. Okay.
Mm-hmm.
And you have to remove the last element of the array, the first and the second, right?
Mm-hmm.
But your to remove will be on the very far right. You remove the element, you shrink, and then your to remove is out, and at that point you remove from here. When you remove from here, you don't have to remove 3 from current, but only 2. So you have to do this not only there, but for every time that we do a remove, we have to check if to remove is less than current and do a minus 1. But we are doing that only in one monolithic step there, and we have to split it in a 4. Oh my god, indexes.
There is probably a nicer way to do this, but whatever.
I'll link in the list.
Yeah, which probably we're gonna have fun doing it in the next episode,
Okay,
right?
that is just an empty array. Can you declare with zeros? I think
actually, yeah, we can just do 0, 3.
0, 3. We are overwriting it.
264. There you go.
Now we loop 3 times
for
underlining 0, dot 3. Cool. Pick up, no, not underline E, because we need that number. Now pick up of E is equal to self cap remove to remove copy the line 30 basically.
Yes.
Yes.
Now this if statement goes here.
If to remove modulo self cap len, you need to keep the modulo at this point there.
Here on this side.
Yeah, on that side. Self caps len is giving priority to the modulo, not to the.
I hope so, but let's put parentheses just in case. I mean, it wouldn't make sense otherwise.
Okay, I think that in this way we are preventing the out of bound that I predicted there. Let's try again. No, it's not liking 0, 3.
Needless range loop. There is probably a more idiomatic way with mutable pickup, I think. But doesn't matter. I mean, we can refactor later. Let's see if this works. Oh, exploding, hopefully in the last line.
Where? No. It's not the last line.
What line is in line 137. Still here. So we are selecting 4 rather than 7. And what is our state? 4 rather than 7. I'm starting to think that maybe it's best if we implement linked list, because we are going to clean up all this logic.
Because with indexes is a lot of edge cases. Because you are implementing a circular buffer on top of a vector.
Yeah, exactly.
Moving stuff around, that is terrible because. So let's do this with a linked list.
Do we have time now, or I do have other 10 minutes, so we could probably try to use the time.
10 minutes.
And I mean, we stop where we need to stop.
Okay, let's try in 10 minutes.
Okay,
But
so
we have to change a lot of stuff because we have to change the parser also.
yes.
Okay, the idea of the linked list is the following one. We are always having the numbers that are different. So we can use a vector where the index is the value, and the value of the vector of that index is the next value.
Mm-hmm. We can probably do a super quick, let's call it list, right? Where we have values to be an array of sides, whatever we decide. The sides is const. How was it? Const t, two sides, I think. Generic. And the values is gonna be yeah, we want to say U64 of t, right?
Here we have sizes because we are pointing to the next one, but it's we complain later. It's not a problem.
U sides here.
Yeah, because you have an index that is giving you a number. That number is another index that is giving you another number. That is another index that is giving you another number. And in this way, you have your circular list. Now, the from string of this guy is a little bit more tricky than the one that we have down there.
Yes.
Because for our input string, we need the current value and the next value. So we have to look at two chars at the time. And we have to say that values of this guy is equal to this guy. Then we go to the next couple, that is the one from before and the new one. And the values of this guy is equal to this guy. And then we have a new one that come in, and so on. And the last one and the first one are the value of the last one is equal to the value of the first one. The value at the index of the last one is equal to the value of the first one.
Okay, here Thomas is suggesting either.window, which I'm not really sure.
Probably window is 2 elements. And they
or you can probably specify the size of the window.
The only stuff is that the last one must match with the first one. I don't know if window is doing that.
Okay, what I was thinking is that this linked list is something we can think as its own module and add a bunch of all the helpers we need, and then we
can do that.
Basically use that.
Okay. Do you want to do this now or next time? Because we are already at 1 hour and a half, I think.
Yeah, let's probably stop here, but we know what to do for next time.
Yeah. So the solution working on the vector with indexes is a mess of if edge cases and dropping around. So we go for a linked list implementation. At this point, if you want, I can show the slides.
Yes, let's show that very quickly. So we will continue from there next time.
Give me a second. How does it work here? Okay, so this is a sequence. Can you see it?
I can see it, yeah.
Okay, this is a sequence 3, 2, 6, 5, 1, 9, 4, 7, 8. I don't know if it's the one in the README. I don't think so.
No, I think it's different, but I guess it doesn't matter.
Array of 0 is not used because we don't have a 0 in this. And array of 3 will point to 2. Array of 2 will point to 6. Array of 6 will point to 5. And so on. Array of 1 will point to 9. Array of 8, that is the last one, will point to 3. This is our current, and there is other pointers. The first step is changing this array only in 2 places. 2 elements must be changed. So there is no array shift, there is no array slicing, there is no insert, no remove. It's just array of 3 go to 1 here, and array of 5 go back to 2. This is not even needed, but just to be fine. At this point, you have the linked list without the 3 elements that you removed, and you search for the destination in this sub list, in this sub linked list. You find 1. Okay, this is my destination. Now you have to insert the numbers back in place. To do this again, you change only 2 elements of the array. That is 5 that we point to 9, that was previously pointed by 1. You see, previously 1 was pointing to 9, so now array of 5 is equal to array of 1, and you link this way. And array of 1 will go to 2. That was what was pointed here at the beginning from array of 3. So you have to just keep track of one pointer, basically, in a variable. At this point, you have your linked list that is the next state. The current is becoming the one on the right of 3, that is 1, because array of 3 is 1. So your current becomes the value of array of current is equal array of current. Easy. Sorting them again, you get to this linked list, and you go on with your 100 steps or 10 steps, and you get to your solution.
Yeah, I think we could, not to complicate the problem, we could implement that linked list and then do an impl where we provide a bunch of helper functions to take out things and add them in certain positions. And then our business logic will be much easier.
Yeah. And also, representing the linked list like this is only doable because we don't have repetition, because the numbers are all unique. The only waste is that array of 0 is not used.
Yeah. Otherwise, we will need to go for a more traditional linked list implementation with references and pointers, which in Rust is notoriously tricky.
We luckily, working with numbers, so we can use the indexes as pointers.
There is another question from Tommaso, which I think it makes sense. Maybe we didn't explain all the requirements. Like, why not a map?
We can use a map too. Is exactly the same, because the syntax is exactly the same. The problem is that an array is a vector or an array, because we can even allocate an array, because we know that we have 10.
And we have all the numbers. It's not going to be a sparse sequence.
Yeah, it's not sparse, and we know the size. It's way faster. Map is lower. But yeah, map works in the same exact way, because in the end, a map of number to number, same as exact. The problem, like Luciano say, is not sparse, is dense, except for one location, array of 0. And it's not even a vector, it's an array. Yeah, the hashing is kicking you in the... the hashing is not the fastest one.
Yeah.
Instead, going in array in a specific location is a super fast operation in assembly. So next time we can re-implement part 1. We can keep this one just to remember how hard it was to write it, and without even having.
Yep. I will also do a commit later on where I make sure no test is gonna go on fire.
Yeah, we still have to look around in the pointers, logic, arithmetic.
Cool. Sounds good. Do you want to do the closing, Roberto?
Yes, if I connect the brain. Okay, let's wrap it up. You can find the recording on YouTube. The link is on Twitch in the About section. If you're watching this on YouTube, sorry. And we do live streaming on Twitch every Monday, 5 p.m. UTC. Make sure to check the Twitch link in the YouTube description. Give us a follow and the usual stuff.
And repository is here for contributions.
The repository is at the banner. Feel free to leave us comments and open PRs. Everything is well accepted. We are trying to learn Rust. We don't accept the solution to be the cleanest or more idiomatic ones. If you know better ways, tell us. Thank you for all the suggestions and the collaboration in the chat. Are we going to raid somebody?
Yes. We are gonna raid. We have a choice to AWS reInvent or probably JavaScript stuff with James Langsdorff. What do you suggest, Robert?
As you want.
Let's go with JavaScript stuff.
Thank you. Bye, and see you next time.
Bye, everyone. Well, raid starts in 5 seconds.
So again, wave until it starts.
Bye.